Okay, well, good evening or good morning, everyone. Thanks for dialing in today for our April special edition, special time meeting of the Friends of Lunar Volatiles. And so this month we have Dr. Honglei Lin. Honglei is at the Institute of Geology and Geophysics at the Chinese Academy of Sciences. And he is going to be talking to us about a recent paper that the Chang'e 5 team published on the in situ detection of OH and H2O on the moon. So I will remind everyone, if you're not speaking, please put yourself on mute. And I actually, before I hand it over to Honglei, I also want to welcome Steve Liu, who of course was at LPI a few years ago and is now back in China and part of the Chang'e 5 team. And then Shuai Li is also a co-author on this paper, and so he's joining us from Hawaii. So welcome to Honglei, Shuai, and Steve. And Honglei, I will hand it over to you, and I will put myself on mute as well.
Okay. Thank you very much. Yeah, hi everyone. Yeah, I'm Honglei Lin from the Institute of Geology and Geophysics, Chinese Academy of Sciences. I'm very glad to have the opportunity to give a talk in Friends of Lunar Volatiles group meeting. Yeah, I'm in a hotel now, and my internet is not very well, so I'm going to turn off my camera to make sure the internet fluent. That is okay, Percy?
Yep, that's fine.
Okay, cool. Yeah, and my primary research interest is hyperspectral remote sensing, especially the spectral analysis for the Moon and Mars. And today I'm going to I will talk about the detection of water on the lunar surface by the Chang'e 5 mission. And this work was finished by the cooperations with my colleagues from National Space Science Center, CAS, University of Hawaii, and Nanjing University. And my talk has 6 parts. First, I will briefly overview the Chang'e 5 mission. As we all know, the Chang'e 5 is a sample return mission. The spacecraft contains a sender, a lander, a returner, and an orbiter. The combination of the lander and the sender touch down the lunar surface to conduct in situ exploration and the sample collection. Then the ascender takes the samples and leave the lunar surface and then dock with the orbiter. Finally, the returner get back to the Earth with the samples. The Chang'e 5 mission has 2 main scientific objectives. The one is to carry out in situ exploration in sample collection area, providing the geologic context of the samples and establishing the connection between the in situ data and the lab data. And the other one is the systematic and long-term study of the samples in the ground lab. And in order to achieve the objectives, 4 scientific instruments were carried by the Chang'e 5 lander, including a landing camera, a panoramic camera, a lunar mineralogical spectrometer, and a lunar wavelength penetrating radar. The 2 cameras are used to explore the surface exploration, the surface topography and the geological structure. The spectrometer is used to survey the compositions of the sampling area, and the radar is used to detect the subsurface structure at the landing site. And the Chang'e 5 collects the the lunar samples in two ways. The one is soil core drilling. The other one is soil and rock fragment scooping. The Chang-5 spacecraft was launched on November 23rd, 2020, and landed on the moon on December 1st. Sample collection was then finished the next day. About 2 kilogram lunar samples returned to the Earth on December 16, 2020. This is the first sample return mission since the Soviet Union's Lunar 24 mission in 1976. And the samples were collected from northern Osner's Prosteron basin of the moon, about 43 degrees north latitude, higher than all the previous landing missions. And this is the picture of the landing site. We can clearly see the disturbance of the lunar surface by the lander exhaust. The Chang-5 landing site is a young mare basalt region based on the remote sensing mapping, which is confirmed by the sample analysis in the lab. And the age of the basalt at the landing site was modified to be about 2 billion years younger than all the known lunar basalts. And the northwestern mare unit of the landing site was stated as inborn age from crater counting and it exhibits low titanium content. And the landing region is within the young arytothanin mare basalt unit, and it contains a moderate amount of titanium. And the mean thickness of the young mare basalt at the landing site was estimated to be about 50 meters based on crater classification method. And underlying layer exhibits similar features as the low titanium mare basalt unit in the northwestern region of the landing site. Above two parts are the background of the Chang-5 mission, and as I said above, 4 instruments were carried by the lander to in situ explore the sampling area. The spectrometer OMS is capable of detecting water, providing us the opportunity to in situ study water on the lunar surface for the first time. The LMS has 2 operating modes, including the hyperspectral mode and the multispectral mode. They have the same spectral range from 480 to 3200 nanometers, and the spatial resolution of the image is about 1 millimeters per pixel. And they have different band numbers. The hyperspectral mode data has more than 500 bands, and only a few spots were measured. And the multispectral mode data only has 20 bands, but the whole sampling area was measured. We used the hyperspectral data to assess the water content on the sampling area. The MS is installed on the side panel of the lander and located below the lander's robotic arm, and observed about 2 meters multiply 2 meters area, where it's about 2 meters away from the lander center. The area marked as the white box is the observing area of the hyperspectral mode of LMS. Besides the reluctance at the landing site, a rock was also measured, but unfortunately, the rock wasn't brought back. And the observing time of the measurements is from 10 to 10:30 a.m. the local time. So we are unable to analyze the variation of water features with time because the observing time of each spectrum is so close. And this is the spectral observations of the Chang'e 5 lander. The left pictures are the field of view of LMS, and D11 is the rock, this one. And we can see apparent thermal emissions on the reflectance spectrum due to the high temperatures of the lunar surface. The spectral uplift at the wavelengths longer than 2 micrometers. Even so, the absorption features at around 2.85 micrometers can be observed in some of these spectral. In order to better constrain the water features, the thermal contamination on the reflectance spectrum needed to be removed. An empirical thermal cracks model proposed by Li and Melikin in 2016 has been well applied to cube data and mapped the water distributions on the lunar surface. They established the relationships between the reflectings at 1.55 and 2.54 micrometers of the lunar samples that measured under room temperature. The 1.55 micrometer isn't affected by the thermal radiations, and 2.54 micrometers is. And then the true reflectings at 2.54 micrometers of the measurements can be predicted using this relationship. So the excise readings of the measured spectral in comparison to the predicted readings can be attributed to the thermal emissions, and thus the surface temperatures can be estimated according to the Planck function. And finally, the thermal emissions at all wavelengths can be calculated and then removed using the Kirchhoff's law. 1.55 and 2.54 micrometers were used because they are beyond the absorptions of primary compensations on the lunar surface. And we also applied this model to correct the Chang'e 5 spectrum. Before the correction, we have tested the applicability of the empirical thermal cracks model using the spectral data of the Chang'e 4 rover, which is still running on the far side of the moon. The rover was stationary on the lunar surface in the 10th lunar day of Chang'e 4 mission of the mission operations, and measured the spectral of a same spot at different local time in a lunar day. And we can see the spectral method close to local moon have larger slopes at wavelengths longer than 2 micrometers. We can see that the data don't gradually change over time. This is probably due to the low signal noise ratio of the spectrometer. And we assume the spectral method in the local afternoon have a few thermal contributions, and we found a good relationship between the single scattering albedo at 1.55 and 2.38 micrometers. Yeah, it should be noted that it's ideal to use the longer wavelengths that beyond the mineral absorptions to build the relationship. However, the channel data only covers spectral range up to 2.4 micrometers. But the spectral, we can see the spectral at the measured spot are rather flat at around 2.38 micrometers. So it's valid to use this band to do this work. And after thermal correction, the spectral beyond 2 micrometers are consistent with those unaffected by the thermal emissions. And the results show that the empirical thermal correction model can be well applied to the data of channel emissions. Actually, the channel 5 spectrometer primarily inherits the technology of the channel 4 spectrometer. And this is the corrected channel 5 reflecting spectral. We can see the obvious absorption at around 2.85 micrometers in some spectral, which is related to hydroxyl and or water molecules. And we calculated the spectral parameter aspect at this band to calculate the water content. The aspect exhibits a strong linear correlation with the water content. And the aspect is a function of single scattering albedo, which can be calculated using Hecke's model. But the slopes of the trend line between the aspect and the water content depends on the particle size of the reagents. So we assumed that the particle size of the reagents at the channel 5 line site as 60 to 80 micrometers, which is similar to the particle size of the Apollo samples at the 6 Apollo missions. This is also similar to the particle size of the channel 5 soils released after. Oh, okay. This is the water content, the estimated water content at the sampling area. The reagents at the channel 5 sampling area contains less than 120 ppm water. If assuming the rock surface has been space weathered to fine particles similar to the reagents, the rock contains about 180 ppm water. The uncertainty of the estimated water content from aspect is about 20%, and the detection limit of the spectrometer is about 30 ppm based on its signal noise ratio. And then we can see from this picture the distribution of the water content in the sampling area is not homogeneous. due to the effects. This is probably due to the effects of rocket exhaust. We can see that the spot D12 shows higher water content. Generally, the top layer of the lunar raglands is probably more space weathered and thus contains more solar wind origin water. And the spot D12 has more water. We think there are two possible reasons for this. The one is the deposition of fine particles blown by the rocket exhaust. These fine particles were transported from the topmost surface below the lander, and this can be supported by the phase curve is extracted from the multispectral data, which shows higher albedo at spot D12. And the other one possible reason is that the raglands at spot D12 is shielded by the rock and was slightly affected by the rocket exhaust. Now we can see in this picture we can see these little rocks can block the bloom, the rocket plume. But unfortunately, no clear pictures like this were taken around the sampling area due to the imaging direction of the landing camera. And so the where the water at the sampling area came from, the sample analysis in the lab indicates that the mantle source of the top 5 results is very low, lower than 5 ppm. So water in the raglands is probably mostly from solar wind implementation, similar to the Apollo raglan samples. This is also confirmed by the hydrogen isotopes of the top 5 samples measured by my colleagues. And the rock is more complex. The water estimation, the water estimation is relying on the particle size, but it's very difficult to know the grain size of the rock. And the compositional analysis suggests the rock was transported or excavated from the older low titanium basalt unit. It has more water than the raglands if we assume the rock surface has been space weathered to fine particles. The excess water may come from additional sources such as the lunar interior, but the estimated water content of the rock drops to about 70 ppm if we assume a larger particle size of the rock. The current models are developed with powder samples. It may bring larger uncertainties when applied to the rock samples. So when new models for estimating water content of the rock samples become available, it will be necessary to revisit the water content of the rock to confirm whether lunar interior water exists. And we also measured the top 5 samples in the lab with the backup top 5 spectrometer, which is seen with the LMS on board the lander. The field of view of the top 5 backup spectrometer was modified to 8 millimeters to to measure the small amount of samples. And to better avoid the terrestrial water contamination, we put the spectrometer into a glove box. The glove box is under a dry nitrogen environment with water content less than 0.1% ppm. And the pristine samples were opened in the glove box and sieved, and then the spectral were measured. The whole process is under a water-free environment. And this is the reflectance spectral of the top 5 soil samples. The spectral of the bulk soil exhibit flight at around 3 micrometers, and the fine particle and the fine soils smaller than 45 micrometers show visible absorptions at around 3 micrometers. We also calculated the water contents using the spectral parameter of aspect. The water content in the bulk soil and the large particle powder are less than the detection limit of the spectrometer. The water is more abundant in the fine particle soil. This result also supports the solar origin of the water in the rocklands at the top 5 landsat. And the further analysis of the returned samples are still in analysis. We will report the detailed information in the near future. So yeah, in summary, the spectral of the rocklands and the rock were in situ measured by the top 5 lander on the lunar surface, and we identified the absorption features of hydroxyl and or water molecules. We estimate up to 120 ppm of water in the lunar rocklands, which is mostly attributed to solar wind implantation. Interestingly, light-colored and the surface-pitted rock around the lander could be transported from an older basalt unit, and it could probably have more water than the surrounding rocklands, which may suggest an additional source. For example, the lunar interior. The laboratory measurements of the top 5 soil samples indicate that the fine particles contain more water, also supporting the solar origin of the water in the rocklands. Yeah, and the contents of this partition came from these 3 papers. Yeah, okay, that's all I have. Thank you very much.
Awesome. Yeah, thanks so much, Honglei. Very interesting work and excellent presentation. All right, so we have some time for questions. So folks, if you have questions for Honglei, feel free to raise your hand or put them in the chat. And I see we have a question from Michael Poston in the chat, and Michael asks, what was the temperature of the moon when the spectra were collected?
Yeah, you know, we don't have we don't direct measure. We didn't directly measure the surface temperature, but we estimated the surface temperature using the spectral. It's about about 360 to 70K.
Awesome, thanks.
Yeah.
And I see Yuchi has his hand up.
Yeah, Honglei. I noticed you mentioned that the mental source of Chang5 samples, the source is the water abundance is around 1 to 5 ppm. But also according to whose paper, I think that although the mental source of Chang5 source is pretty dry, but doesn't mean the basalt is dry, because if you notice Tianhen's paper, the partial melting and large degree of fractional crystallization will increase the water abundance, make the Chang5 source itself has a relative high abundance of water abundance, although the mantle is dry. I think maybe the abundance is several hundred ppm. So I think this is a point. Yeah, and what's your perspectives? Because I noticed you mentioned the mantle is dry, but you don't mention the basalt itself, its abundance, probably from petrologic or geochemistry work.
In whose paper they measured the water contained from I remember it's a habitat, from the habitat, and then calculate the water contained in the mantle using I don't know. I'm not the expert in the geochemistry, so but the main source is it's dry. The basalt is not dry. I think it's
yeah, Jim, do you have some point here? Because in my understanding, the later magma evolution will increase the volatile content in the basalt, although the mantle is dry. And Jim is the expert here. Jim's not here. So the eruption, the essence eruption will and the crystallization of the magma will increase the volatile content, make the basalt itself is not very dry, although the mantle is dry.
Dry is dry side. The basalt is after degassing, so it is dry.
Yeah, the point is like even after partial melting, you can get enriched water in the basalt, but after in the melt, but during the emplacement of lava, it's like there's strong degassing. Like you know, even though you have like a 90% like enhancement, but you can have like over 90% like a degassing. So that's why you know the basalt is also very dry.
But you could also have late stage enrichment based on just decreasing extrusion rate and increase in the volatile content. So that's, you know, that's one aspect too.
Yeah, I guess they have some measurements from retinal samples showing the whole sample is very dry. Well, like you know, Honglei has measured the whole spectrum of the regolith. You can see the spectral feature, where that's pristine sample without any contamination, and a room like an ambient condition. You can see the spectral feature is very weak. So overall, the samples are very dry. Well, it's I think it's hard to know the rock.
Right, so Honglei, we have a question from Dave Blewett. So Dave asks, how did the spectrometer observe different areas on the surface? Did it have a pivot?
Yes, the spectrometer, it can there's a turntable to turn the direction, the observing direction of the spectrometer. So I think the angle is about 40 degrees, or I don't remember the exact values. That I mean it has a pinch angle and how to say. So can you understand what I say?
Yeah, it had a 2-axis pivot, so it could pan and tilt in 2 directions. Yes, thank you.
Yeah, yes.
Awesome. So I have a question. So Honglei, I know you said the Chang'e 5 didn't bring back this interesting rock, but are there any similar rocks in the sample collection? You know, anything which also has like a water content?
Yes, that. No, we have a very small amount of the samples. The total amount of the samples is 1.73 kilograms, and we apply the samples. We can only get less than one grams. So it's hard to find the larger rock fragments in the samples. So now until now I didn't find the very similar rock fragments as the interesting rock in the land side. So I hope we can find some fragments like that, so we can assess the water content in the lab. So we can provide a more accurate water content of the rock, because the water content, the estimation of water content from the spectral is very relying on the model. So yeah.
I see. And maybe related question, but so then from the regolith samples, can you get information about how the water content might vary with depth, or are the samples kind of really from the surface? Like, can you get any stratigraphic information?
You mean?
So, like, I guess when it was collecting the samples, is everything from from like the upper millimeter, or do you have anything that's deeper? And is there a difference in the water content?
Yeah, we can only get the information from the very topmost layer. About few less than few centimeters, and the spectral range of the spectrometer is up to about 3.2 micrometers, and so it can, I think we can get the information from the about I mean the optical depth of the light can penetrate about 1 millimeters. So we don't know the information in the subsurface. Only the materials excavated by the impact event, and we can know the information of the subsurface. Yeah, so the water content of the surface and the subsurface need to the combination of the background of the area.
Okay, yeah. And I see Abigail Flom has a question in the chat. And Abby, did you want to unmute and ask your question? Because I know you've been looking at the Chang'e 5 landing site through telescopes as well.
Sure. Yeah. Actually, Chai and I had an interesting conversation about this at one point too. But I was just curious about how well you know the distribution of the dust around the site after the landing, because you were saying that the smaller size fraction had more water content. So I was curious how well you know that distribution, and also just generally how disturbed the various regions you showed of the surface are.
Yeah, the distributions of the fine fine particles blown by the lander may be a few meters from a few meters to tens meters. You know, we don't know the exact the distributions, but we checked the phase curve, of the
Right, you're
sample
showing
area.
the diagram. Yeah.
Yeah. If the sample area is homogeneous, the phase curve will be like the red line. No, but the area with a higher water content shows hair albedo, suggests the particles at this area is finer than other areas. So we guess if in this case if this is the case, we guess the fine particles may be deposited in this area.
Oh, okay. That's really interesting. Thank you.
Yeah, and I really like this photograph. Like it's really cool to see the shadowing effect from the small rocks in that rocket plume image. Very, very cool. I have another question. So I know I guess the closest orbital data set we have is maybe the M-cubed, and I know that the M-cubed data cuts off right at 3 microns, but in general, are the in situ measurements consistent with the orbital constraints that we have?
Yes, the reflecting spectral of the Chang'e 5 is comparable with the M-cubed data. But the spatial resolution of the M-cubed data is about 100 meters per pixel. The spectrum is the average of 100 meters multiplied 100 meters. The reflected values is comparable, but the in situ data can measure can measure the surface in fine scale. So in the M-cube data of the landing site, there's no obvious absorptions at about 3 micrometers, suggesting the landing site is also wet or dry. So yeah.
Yeah, it would be. So the instrument is on the like it's still on the moon, right? It's not in the part that return to Earth?
Sorry.
The instrument is still on the moon, right? It's on the lander part
Oh,
of
yeah,
the.
yeah,
Okay.
yes. No,
And-
when the rocket lift off the surface, the ascender lift off the surface, the rocket will, the fire of the rocket will destroy the lander, so the instrument can't work now.
Okay.
Yeah.
Okay. Yeah. No, it would be cool to put it on a rover and drive around.
Yes.
Yeah.
Yeah.
Yeah. No, very, very cool. Do we have more questions for Honglei?
So partly a question for you, maybe, just what you know about rocket exhaust and temperatures, and do you expect any of the, exhaust products would be implanted or could stick around very close to the landing site?
Yeah, good question, Dave. Like I see we have Phil Metzger online as well, and I know Phil has done lots of experiments on this as well, so maybe he could chime in as well. But yeah, so the simulations I've been doing, I've been looking at kind of deposition really far away from the lander, and so the data Honglei is showing is from within a few meters of the lander, which I haven't really modeled, but also it does make me wonder if like there's a transition between net loss of material due to the rocket exhaust and net deposition of material from the rocket exhaust. So for instance, I wonder if you went further from the landing site, maybe you might see some exhaust water vapor that was deposited over the area. But yeah, it's a good question, and yeah, I'd be curious to know what Phil and I know Michael was asking about the temperature. And like it seems at 370 Kelvin, H2O, I think would probably be gone. Though OH could, solar wind OH could still be retained.
Hi, Parvati. So I can say a little bit about it, I think, maybe. So to my knowledge, nobody has modeled this particular situation. I've done some modeling of the gas diffusing into the soil underneath the lander. But this size lander, I have not looked at it in particular. But like for a larger lander, there would definitely be quite a significant quantity of gas diffused into the ground, centimeters deep into the soil. And then after the engine shuts off, it will be coming back out. And I think that with a sensitive instrument, you could measure it for days, coming back out of the soil. I don't know, though, the concentration that will stick around on the surface and be measurable. I don't know that anybody's measured that. During the talk, you mentioned that in the pictures, you could see the wake behind the rocks. And so the backside of the rocks would not be as exposed directly to the plume. And I think that's correct, but I would expect some of the water to still get on the back of the rocks because the Boltzmann distribution has a very long tail, and gas will turn corners around solid objects in vacuum because of that. The water molecules bouncing inside the advection, there will be molecules that bounce upstream faster than the advection flow. And so there is some water coming back to the backside of rocks. but I don't know that anybody's ever modeled it or measured it. So it may be completely insignificant. I just don't know.
Yeah, so this is Michael Poston. I can follow up on the thermal part. At 370 Kelvin, or even maybe 350 Kelvin or lower, you're going to lose all the water within the surface absorbed water within seconds to minutes, or have a very small amount below the detection limit. I think the detection limit was quoted as 30 ppm here. So yeah, you'll be below 30 ppm by this temperature, I would expect. So I don't think there's any surface absorbed H2O in these samples or in these spectra. I'm actually, and I've said this to many people over time, I keep wondering why people call this 2.8 micron band OH/H2O, because I think there's strong evidence that it's almost entirely from OH. So surface and solar wind implanted hydrogen reacting with oxygen, as was suggested by the speaker, I think is probably most, if not the only thing being seen here.
An interesting thought to jump on that. I know I've heard people talk about potentially modeling like OH versus H2O if you can see the full band, which I know we weren't doing with M-Cube because it cut off at 3 microns. But if we can see out to 3.2, maybe we can say with modeling that, oh, this is just OH causing this spectral feature, or oh, it looks different.
Yeah, Honglei, did you have thoughts on that? Like, so since you go out to 3.2 microns, can you tell, if is it OH or is there really any H2O?
Or do you plan to model that?
Yeah, if we want to distinguish what features is OH or H2O from the spectral, we need to extend the spectral range to at least 3.6 micrometers. In this way, we can get the whole envelope of the spectral to accurately estimate the absorption positions to determine whether it is OH or H2O. Yeah, this is from the spectral view.
Yeah, I think the slide a little later in the talk showed, I think, some laboratory spectra, and the 12001 sample actually had what to me looked like a really good H2O band. I assume that was not original to the 12001, but I could be wrong.
It could be like surface absorbed atmospheric water. I can follow up a little bit on that. So about a discrimination from H2O and OH based on the 3 micron band. I've done some preliminary analysis, use my samples. Like, it turns out when the water content, like a molecular water content, is a little bit higher, it's doable. But you can see at this case, it's like extremely low. It's like 100 ppm. So it's like, even though you have some little more water feature, it will be buried in the noise because it's too weak. Yeah.
Yeah, that makes sense. At that abundance, it would be really hard.
All right, I have one final question. So Honglei, how long after the landing were these measurements taken?
How long? It's before the spectrum measurements were performed before before the sample collection. I think it's I don't know the exact I don't remember the exact time of the landing time and the sampling time, you know. So I will check this and then send to you. Okay.
Yeah,
Yeah,
sure.
I don't know the exact time now. No.
But like, I guess probably, you know, like a few hours.
Yeah.
Okay. Yeah. Interesting. Do we have time for maybe
I had
one?
one quick thing,
Yeah.
sorry.
Yeah, go for it.
I also wanted to follow up on what Phil Metzger said about the landing exhaust coming out slowly. I agree with that. I think that's likely. I really want to try and simulate it in the lab or see it with the lander that has the right instrumentation. But I don't think that would be contributing to this measurement because that's not really going to have a long surface lifetime as it comes out. It'd be more of a thing a mass spectrometer or another gas phase instrument would be able to detect.
Yeah, thanks, Michael. Okay, so we are coming up on 9 p.m. here on the East Coast. So thank you again, Honglei, for making the time. Thank you for joining us. You know, very exciting work, and yeah, look forward to seeing the future sample analysis results, and you know, maybe next time you can go out to 3.6 microns and put it on a rover, and we'll have even more exciting results. But thank you so much. Excellent presentation, and good to see you as well.
Yeah.
And
Thank you all.
Yeah. All right. Thanks, everyone. Take
Honglei,
care.
great to see you. Great to see you, Honglei.
See you, everyone.
Bye.
See you
Bye.
soon. See you,
Bye.
Troy.
Bye, everyone.
See
See
you,
you
Jim.
next month.